All right. Well, good afternoon, everyone. It's really nice to be back in Cambridge, where I did my PhD, and it's really nice to have the opportunity to talk to you about some work I'm very excited about that I've been doing with Kevin Costello and his former PhD student, Qiyu Zheng, who's now at Harvard. Right. So let me start with just an introduction. So I probably don't need to tell this audience that the Self-Yang-Mills equations are integrable in the sense that they can be solved formally using the Penrose-Ward transformation. But it was only fairly recently that Kevin noticed that the Ward transformation is actually anomalous at one loop. And we've kind of heard a bit about that earlier in the day, and I'll review this in more detail in a moment. But probably this is maybe the most important part of the talk. I'm not sure this is as well known as it should be. But yeah, so the Ward correspondence fails at loop level, but it can be fixed, and it can be fixed in an interesting way. So then he and Natalie showed that if you cancel the anomaly, then there exists an abstract chiral algebra whose correlators compute form factors. So Natalie spoke a little bit about that just now, and I'm going to spend quite a bit of time reviewing that, but from a slightly different perspective and focusing more on the loop corrections. So this chiral algebra, it's not just abstract nonsense. It really gives you an advantage when computing amplitudes. So Kevin and Natalie computed certain one loop, one minus amplitudes using the chiral algebra in certain very special gauge theories, which are nevertheless non-supersymmetric. I think probably those one loop, one minus amplitudes were known, or at least could have been computed if people knew that they were something interesting to compute. And then following that, Kevin computed a two-loop all plus amplitude in one of these special theories. And the remarkable thing is that was done for an arbitrary number of external particles, and it was recently verified, at least at 4 points, by Lance Dixon and his student Anthony Morales. Of course, we also heard from Natalie that you can use these chiral algebras to compute amplitudes on curved backgrounds, and I'm also going to talk a little bit about that later in the talk. So, in some closely related work, Kevin, Natalie, and Atul engineered a duality between a certain self-dual gauge theory, gauge and gravitational theory on a scalar background called Bern space, and showed that it was dual to a very simple 2D chiral CFT at large n. Now, I mean, that's a beautiful work, and I mean, it sparked a whole, it's a large part of what, the motivation for doing this. But if one were to be sort of unfair and criticize it, one sort of slightly unfortunate feature is that the self-dual theory is a little bit exotic. I mean, maybe it's actually less exotic than it first appears, but it's not something that one would immediately recognize.
Careful, you might make an episode.
It would be really nice to modify that and to apply it to something a bit closer to, say, QCD. Yeah, I should say that this was achieved by applying a twisted version of the ADS CFT correspondence to a version of the twistor string. And so in this talk, I'm going to propose a large class of dualities of this type, and they're going to relate certain self-dual gauge theories with massless Farrell fermions on a range of self-dual backgrounds to the large n limit of a 2D chiral defect CFT. So that's a 2D chiral CFT living in some higher dimensional space. Okay, so I'm going to start with a little bit of review. We've heard a lot about some of these ideas, but I'll probably go a little bit faster. So it's probably a good thing that we've seen them earlier. So of course, the Self-Yang-Mills equations are a condition on a connection on a 4D space, which just tells us that the curvature of the connection is self-dual. I should probably stop here and say I'm going to be working in Euclidean signature, as we've heard a lot today. All of the amplitudes that I'll be computing will be rational objects, and so they can be analytically continued to other signatures. And that's just essentially a feature of working with these sort of holomorphic theories on twistor space. So I'm going to be talking about quantum field theory. So I want to write down a Lagrangian for the self-two Yang-Mills equations. And the only way to do this, which preserves Lorentz invariance, is to introduce a Lagrange multiplier, an extra degree of freedom, and then impose the vanishing of the anti-self-dual part of the curvature with a Lagrange multiplier. We saw this Lagrangian earlier. And crucially, of course, this two-form has to be anti-self-dual. And one of the most interesting things about this action is that you can deform it to get full Yang-Mills, at least up to a topological term, the theta term. And to do that, we just have to add this trace b squared, and then integrate out b, which will land us on f plus wedge f plus, which differs from f wedge f by this term. So I'll be computing amplitudes. Of course, in Euclidean signature, a massless momentum would have to be 0. And to evade that, we're going to work with complexified scattering states and complexified momenta. And that means I can express them in terms of a left-handed spinor helicity variable and a right-handed spinor helicity variable. And these are the scattering states I'll use. And self-dual Yang-Mills, so just this EF type action, is an extremely simple theory. So the only diagrams you could write down are tree diagrams with some number of pluses, I should say connected diagrams, tree diagrams with some number of pluses and one minus coming out. You can, or one loop diagrams, so just loops with pluses coming off. Of course, you can take one of these trees and bung it into one of the edges of the loop, but broadly speaking, these are the only two things you can get. And it turns out that the trees will vanish. The loops don't. And the vanishing of the trees, there are many ways to see it. It's a consequence of supersymmetric Ward identities. There's some clever tricks with choosing sensible or clever gauges in the full gauge invariant amplitude. But one way to see it is from integrability, so from the existence of the twisted construction. And the fact that these amplitudes are not vanishing is kind of signaling that something's going very wrong with the twistor theory at loop level. Okay, so this slide is kind of redundant for this audience. Of course, the self-two Yang-Mills equations can be solved using twistor theory. It's the Ward correspondence. But in the unlikely event that someone here doesn't know what twistor space or flat space is, it's just going to be O1 plus O1 over CP1. In the usual way, points in complexified space-time correspond to degree 1 rational curves. Those corresponding to the Euclidean slice are fixed under some anti-holomorphic involution, and that gives us a diffeomorphism, smooth diffeomorphism between the twistor space and R4 cross S2. And of course, solutions of the self-two Yang-Mills equations on this 4D space are equivalent to holomorphic G bundles on twistor space, which are trivial on twistor lines, together with some stuff about reality conditions.
Don't feel shy about telling people things they already know. It makes them feel comfortable.
Yeah, I think it's going to get worse, don't worry. Okay, so as a classical field theory, we can rewrite that self-two Yang-Mills theory as a theory on twistor space. This is kind of just doing the Ward correspondence at the level of the action. So that theory has got dynamical fields of partial connection, which determines an almost complex structure on a G bundle, and it will determine a complex structure if it squares to 0, which is the vanishing of this curvature type object. And we can write down an action for it, or I guess Witten wrote this down, I suppose, and Lionel showed that it really does descend to self-two Yang-Mills on 4D space, just by taking that kind of curvature object and wedging it with whatever form is appropriate to make this thing make sense. And so what Lionel showed was that if you partially gauge fix using the equations of motion, which have sort of components in the P1 fiber direction over your 4D space, then you can recover a 4D connection and an anti-self-dual 2 form. And in fact, these two actions are equal to one another off-shell. But this theory doesn't exist at the quantum level. And the reason for that, I mean, is precisely that there's an anomaly. The gauge variation of this diagram is non-zero. So we're in 6 real dimensions, and in 6 real dimensions, perturbative anomalies come from box diagrams. That's the first place you'll see it. And it's maybe a little bit surprising that a gauge field is contributing to anomaly. We'd usually think about anomalies as being associated to chiral fermions. But on twistor space, everything is in a sense chiral because it's holomorphic. So all fields will contribute to anomalies. And it's kind of a nice idea to imagine, well, what could we learn about quantum field theory, self-dual Yang-Mills at the quantum level, if we fix this problem and got a genuine field theory on twistor space. So one way to cancel this anomaly is just to make the theory supersymmetric. But this is kind of an unsatisfying thing to do because it kills a lot of the most interesting loop amplitudes. So for example, in a supersymmetric theory, one loop, one minus, and, well, sorry, all one minus and all plus amplitudes vanish. And these are the things that are closest to the self-dual sector. So if you want to actually compute an amplitude, that's not going to be much. It's going to be very hard to do it if you've cancelled the anomaly with supersymmetry. Kind of remarkably, there are lots of ways to cancel the anomaly which don't involve making the theory supersymmetric. One such way is to choose your gauge group to be SPK and to couple to massless Bar fermions. So I need 16 fundamentals and 1 traceless antisymmetric square. And I'm going to call this theory in particular, but also any theory of this type where you choose appropriate massless fermions to cancel the twistorial anomaly, a self-dual QCD. I should say, of course, there is no value of k for which this will be SU3, but hopefully you don't mind me calling it that. So cancelling this anomaly, on space-time, just cancels the one loop plus amplitudes. So these amplitudes, they're not a problem in the 4D theory. But what this does mean is that this theory is in some sense completely boring, right? It's got no amplitudes at all, but it's kind of got no amplitudes in an interesting way. Okay, so Natalie mentioned in the previous talk that if you're in this happy situation when you have a genuine holomorphic theory on twistor space, then there's a chiral algebra whose correlation functions compute form factors of the theory. And in this case, that's going to be the self-dual QCD. So I'm going to unpack this statement a little bit. Fortunately, you've already been sort of introduced to it a little bit. So a form factor is just an amplitude in the presence of a local operator. And probably the most interesting local operator we can think about immediately is the operator trace b squared. And that's because that's precisely the operator we need to take self-dual Yang-Mills and turn it into full Yang-Mills. Of course, you need to introduce it an arbitrary number of times, but even introducing it once is a good start. We can start to compute some amplitudes. Also, I mean, these are really the most basic objects we can compute in the theory, because the amplitudes actually all vanish. So these are sort of the first interesting things that one can find. So I've illustrated here some Feynman diagrams contributing to the trace b squared form factor. So the first diagram is a tree, which is contributing to the 4-point MHV amplitude. Here we've got a 1 minus. So I should say that these form factors are actual amplitudes in the full Yang-Mills theory. I need to emphasize that. All right. So how does this theorem work? So the first thing I'm going to do is I'm going to introduce an inhomogeneous coordinate, lambda, an inhomogeneous coordinate z, which parameterizes the left-handed spin of helicity variable lambda. And then we can write down the following dictionary. So this chiral algebra, or chiral CFT, again, I'm a physicist, I'm not going to make a distinction between those things, lives on the left-handed celestial sphere, or really the space of this left-handed spin helicity variable. So it consists of a bunch of states which depend on that left-handed spin helicity variable. There's going to be an infinite tower of these states for every field I have in my theory, and it's got 2 indices m and n, which are non-negative integers. And these correspond to soft modes in the 4D gauge theory. So those are polynomial solutions to the equations of motion. In particular, these polynomial solutions to the equations of motion. You can organize those soft modes into so-called hard generators in the chiral algebra, which I'll write out explicitly on the next slide. And these depend on this inhomogeneous coordinate z and a right-handed spin helicity variable lambda twiddle. And in fact, this is not defined up to scale, so this really contains the energy. Hence why these are sort of soft modes. These come from expanding in powers of the energy. And these are hard modes because they come from summing up these soft modes into an exponential, and the energy sits in the exponential. As Natalie said, this chiral algebra is a little bit strange. It has a huge number of conformal blocks. So conformal blocks are a way of assigning values to correlation functions, so a product of our states. And every way of doing that corresponds to a local operator in the 4D gauge theory. And then the claim of this theorem is that form factors, i.e. amplitudes in the presence of a given local operator, equate to correlators in the given conformal block. So in order for this to make sense, it needs to be true that when this form factor, or amplitude, has a singularity, the corresponding correlator has to have singularity. And amplitudes have singularities, in particular when two massless momenta of the external particles become collinear. And in fact, they have singularities in a holomorphic version of that limit I'll describe in a moment, which corresponds to taking these zi's to become coincident. And so in that way, we can see that the collinear splitting of this amplitude is related to the operator product of the 2D chiral CFT. Does that make sense? Right. So let me be a bit more specific about what the chiral algebra looks like for the theory that I'm interested in, self-dual QCD. So as I said before, the states correspond to soft modes, and there are states for every field in the theory. So there are states for the positive helicity gluons, states for the negative helicity gluons, and then for the left-handed and the right-handed fermions. So here, this A and this B index are color indices. The F and the G indices are flavor indices, and the R and the S are supposed to be indices for the representation of the fermions. And these indices for all these states are just non-negative integers. And they have different spins, which is reflecting the fact that they have, so different spins in the sense of a chiral algebra, reflecting the fact that they have different spins as fields in the 4D theory. So I mentioned that you can sort of sum up these soft modes to get a hard generator, and explicitly that's just given by taking soft modes and summing them up in this way, which depends on a right-handed variable. And these states, the data that this state contains is a left-handed spin helicity variable, a right-handed variable, and a color index. That's exactly the data of a momentum eigenstate, let's say a gluon in this case. So in this correspondence, if I want to compute an amplitude with gluon scattering, I literally put in one of these states for every single particle participating in the process. Okay? So I now want to talk a little bit about the OPEs. So as Natalie explained, you can get these OPEs by writing down a holomorphic surface defect on twistor space and then demanding that it's BRST invariant. But another way of sort of seeing these OPEs is by thinking about the collinear splitting of amplitudes in 4 dimensions. So as I mentioned before, it's really the holomorphic collinear singularity that matters. And what that means is I take the left-handed variables to become collinear while keeping the right-handed variables fixed. Because in the chiral algebra, the states depend, the location at which I put them corresponds to the left-handed variable. At tree level, this can only happen if the two external particles, whose momenta I take to be collinear, are connected to the rest of the amplitude in this particular Feynman diagram, represented by this cross, by a single propagator. And that's because when these become holomorphically collinear, this becomes massless, this propagator becomes massless, and it blows up, because the propagator goes like 1 over p squared with some stuff in the numerator. And this leads to an OPE. J goes to J. That's exactly the OPE we saw in Natalie's talk, although she was describing working on a non-trivial background which changed the kinematics, but the OPEs were under 4. So here I've written it in terms of hard generators. You could expand this in the lambda twiddle variables, and you'd get exactly the formula she wrote down. There's also a plus minus goes to minus, which just comes from the fact that we can draw this diagram as well. A positive and a negative going to a negative. At a tree level, that's all there is. A very, very simple Chiral algebra. But at the loop level, things get a little bit more interesting. So the first thing that happens is that you can get double poles. And this comes from the following diagrams, where the two external particles, whose momenta we're taking to become collinear, are connected to the rest of the amplitude by a propagator, but also by kind of this triangle loop. And the gluons can run through the loop, or the fermions can run through the loop. And this generates a double pole because the propagator blows up, but also loop integrations will introduce poles. And the form of this singularity, it's well known. You can go look up some paper in the amplitudes literature, and it takes the following form. So there's a double pole. So sorry, hopefully that was clear. I should have explained that. These angle 1, 2 variables are just the difference between Z1 and Z2. Whenever there's a 1, 2, this just means there's going to be a simple pole. Hopefully that's clear. Right. What more can we say about this? So the square brackets is, of course, just the SL2C invariant combination of the right-handed spin helicity variables. And there's some factor, some Dynkin index, which comes from counting the number of particles that can run through the loop. And in the particular theory that I was mentioned at the start, this self-dual gauge QCD, it turns out that number is minus a 12. It turns out this is actually very important because it cancels some of the factors in the 1 over 96, which is going to be crucial to make this whole construction work.
So this is now one where you've cancelled the anomaly. So
right. So absolutely right. So I should emphasize that.
In that way.
Exactly. So
you still got the one loop.
Exactly. Yeah. So I should absolutely emphasize. I'm only going to tell you about the gluon OPs because it would just take ages to write out all the other OPs, and they're completely boring. But yes, I'm going to be in the situation when the anomaly is cancelled. And that's going to be crucial because if we weren't, then these OPs just wouldn't associate. This would be a Chiral algebra. Great, exactly. There are also kind of these more subtle contributions. And this is really I think the most non-trivial part about the Chiral algebra. These hide beneath that double pole. And the reason they're so non-trivial is, for example, this collinear splitting and this collinear splitting were well known in the amplitudes literature. But it was also known that the subleading simple pole was not universal. And in a way, this anomaly cancellation on twistor space, it all rests on the fact that when you cancel the anomaly, the subleading collinear splitting is actually universal. So crucially, there's this kind of non-factorization which contributes to the collinear splitting. So here, there's no propagator that connects the two external particles to the rest of the amplitude, but there is a loop integration. And that loop integration generates this simple pole. So I should say, this formula is not a formula you can really get, or at least I don't know how to get it from working on space. You really have to go via twistor space. It's a bit odd because you can see it's a 2 to 2 OPE. That's a perfectly legal thing to have in a Chiral algebra, but it's much more complicated than what we had before, these 2 to 1 OPEs, which are just reminiscent of Lie algebras, or they are just Lie algebras. But here we're really going outside the world of Lie algebras. Another nice thing about this formula is it kind of contains qualitative information. So I've written it in terms of these hard generators, and if you sort of look at this formula, squint at it, you can start to see that it's really telling you some general features about this process. So there's S lambda twiddle 1 and 1 minus S lambda twiddle 1, which means that there's as much lambda twiddle 1 on the right-hand side as on the left-hand side. That's signaling that momentum is being conserved in this process. And in the same way, the same is true for lambda twiddle 2. You can also actually see there's this restriction on the values of S and T. If you think about it a little bit, you'll see that what that's really saying is that sort of more of the lambda twiddle 1 goes to this particle into that particle. So it's really a very qualitative formula, although it's really just telling us some very complicated structure constants for this chiral algebra. So these...
You can do those integrals, well, maybe you have to expand.
Oh, yeah, you could. The reason I've written it in this way is because you can't, it's just some horrendous formula that wouldn't make much sense. But somehow...
But they're nothing too fancy.
They're not too fancy. It's just some functions of m's and n's. It's probably they're not so horrendous as they appear, but somehow, well, they're probably not even that bad. But somehow here you can really see what's, I think, going on in the process. Okay.
Just integrating polynomials.
Yeah, exactly. It's a trivial rewriting of it. Exactly. Yeah.
I was just looking for a polynomial.
No, everything rational. Okay. So these OPEs, together with their fermion counterparts, only associate if the twistorial anomaly vanishes. And in that case, people sometimes call this the celestial chiral algebra. And as Natalie explained, this comes from the universal holomorphic surface defect on twistor space. I'm not sure I'm going to explain exactly this coupling. This is basically the formula for the coupling between the bulk theory on the twistor space and the surface defect. But in any case, demanding BRST invariance of this coupling fixes those OPs that you saw before. Because this thing is really coming from twistor space, it's really living on a twistor line over a point in space, it's not really surprising that if the twistor theory doesn't exist, the chiral algebra doesn't exist. So this sort of explains why you need this anomaly cancellation for this to work. All right, okay, so that was a long review of some stuff that was probably a little bit familiar from some of the earlier talks in the day. Now I'm going to come to the new stuff. Yeah, I guess we've already said this. This is really signaling. So this chiral algebra is in a way the hidden symmetry of the self-Yang-Mills theory, and we're really seeing that the anomaly is a global anomaly in that integrability, the existence of that hidden symmetry.
So what would the little a's and b's in that formula?
Oh, they're just color indices.
No, but there are some...
Oh, these are the twistor fields. Sorry, this is the partial.
Those are just the standard twistor fields.
Yeah, exactly.
And they're just being integrated.
Exactly. Yeah. All right. So now I'm going to explain how to engineer this thing as the large n limit, this vertex algebra, chiral algebra, as the large n limit of a 2D defect CFT embedded in string theory. So we've seen that this self-dual QCD comes from a holomorphic theory on twistor space, the appropriate, and it's anomaly free for this given mass content. And it turns out that this theory is the same as what one gets if you wrap k d5 branes on the zero section of this Calabi-Yau 5-fold, and you twist that theory in the type 1 string with a suitable choice of 32.
That was the easy observation.
Yeah, so when Kevin gives this talk, this is the easy observation, but it's not easy for me, so I've called it crucial. Right, so that's, okay, so why should this be true? So on a stack of KD5 branes, we usually get some supersymmetric gauge theory coupled to some strings going from, well, the D5s to the DD5s, and those are going to describe the fermions that were living in the antisymmetric square of the fundamental. And then, because we're in the type 1 string, we're also going to get some D5, D9 strings, and those are going to describe the 16 files that I mentioned earlier. So these are the D5, D9s, these are the D5, D5s, and this is the gauge theory. Usually that would be some supersymmetric gauge theory, but we twist and land on this holomorphic theory. Okay. So the strategy is going to be to study the holomorphic twist of the type 1 string on this Calabi-Yau 5-fold. We're going to wrap k d5 branes. I'm now going to distinguish them. I'm going to call them k d5 prime branes because there's going to be 2 stacks of d5s on the twistor space 0 section. And that's going to engineer for us the twistor uplift of self-dual QCD. Then I'm going to wrap a further n d5 branes on the fiber over the twistor line of the origin in this Calabi-Yau 5-fold. And then I'm going to back react that stack. So the first stack of KD5s, D5 primes, is just going to be a stack of pro brains. So, whereas the second stack, I'm going to take n to be large and I'm going to back react it. And then there's some sort of general yoga which tells us that the theory on living on that, the world volume theory on the ND5 brains is going to describe the type 1 string in the bulk, and the theory on the D5 prime intersection is going to describe the stack of KD5 prime brains.
Before the holomorphic twist, is this D5 prime configuration supersymmetric?
I don't know. Good question. I'm not sure.
Okay. Asked by a friend who knew much more string theory than I did, but okay, go.
Let's see. Yeah, I don't know. Yeah, so I've indicated where all the brains are sitting. I've preemptively drawn a picture, which is hopefully a little bit clearer, about where they're all living. Is this visible? All right. So here is the space X. Some chalk. This is twistor space, the zero section, and on here we're going to put K D5 primes. On Y, we're going to put ND5s, and these intersect on some CP1. The reason for having them intersect on the CP1 is because the chiral algebra lives on this twistor line over the origin, and we want to get a description on that line. All right, so of course twistor space, fibers over space, 4D space, and the CP1 just sits over the origin, and this process of doing twisted holography is going to give us a dual description solely on Y, this complex 3 manifold. The bulk of that, the world volume theory on Y, so the thing living in the bulk, is actually going to describe the type 1 string in X, and then the theory, the defect CFT living on the CP1, is going to describe the theory on the KD5 primes, which is what we actually care about. This is the, yep.
And this is one of those kind of annoying questions that I think I know the answer to, but have you thought about, in the interest of getting the unitary groups to be...
Oh yeah, absolutely. So you can, this whole story can be done in type 2B. In that case, you'll just get SLK self-dual n equals 1. The reason we didn't do it in type 2B was precisely because in the supersymmetric case, it's harder to compute stuff. But I'm sure it would be an interesting thing to do. And there are some more games you can play there with the other fields in the theory. Yeah. All right.
So you're breaking all symmetry, so you've got a fixed line at the origin, you're breaking form invariance, everything.
Yep, we're going to break translation invariance. So I should emphasize, when you're doing this twisted holography and you take the larger limit, there's going to be some back reaction. And that's going to switch on some background field on twistor space and some space time. And that's going to...
the origin or something, yeah.
Yeah, it's really going to switch on some funny kind of axiom. It's kind of strange. I'll go through that in a moment. All right, is this setup kind of clear? Maybe this diagram helps. Okay, so on the intersection, we'll get a chiral algebra whose states are those of the type 1 string after backreacting, plus the theory on the KD5 prime brains. And on the world volume of the ND5s, we'll get an algebra of operators which describe the states of the type 1 string after backreacting without the KD5 primes. And crucially, the operators in this theory are going to have trivial OPs with everything. So why is that the case? So these are the operators living here, right, in the bulk of Y. So they live they're in a holomorphic theory on a 3D complex manifold, and local operators in a holomorphic theory have to have holomorphic OPs, but they also have to have OPs that are point-like. They have to have the only singularities when the operators come together. And Hartog's theorem tells us that there are no such functions. So that means that they have to have trivial OPs as they come together. And that's absolutely crucial because it means that they form an ideal inside of A and K, and we can quotient. Because we don't want the fields of the type 1 string. We just want the fields describing the theory on the KD5 primes. Of course, we don't quite want to get rid of everything because there's the constant function, but we'll throw everything else out, set everything else to 0. Then we have the following conjecture, that that quotient in the large n limit is isomorphic, so it's the self-dual QCD after backreacting. So I should emphasize the two sides of this are independently defined. Okay? So there's mathematical content in this statement. Sometimes people like to interpret this kind of setup as a toy model of celestial holography. I think it's kind of hard to see exactly what this has got to do with the celestial sphere. And in a sense, the CP1 is the celestial sphere. But in any case, it's some kind of flat holography at least. For a very special self-dual theory, I should say. Okay. So I want to describe a little bit the theory that's living on Y. So it's actually very similar to the theory that lives on twistor space. So it has a partial connection, which is valued in the gauge group SPM, and a Lagrange multiplier field, which will impose the vanishing of this curvature, just requiring that this covariant d-bar operator squares to 0. It's going to have some scalars describing the d5 strings, go from Y to Y here. And there are also going to be some scalars which describe d5, d9 strings. And this is because we're in the type 1 string, we need some space-filling branes. The action of the theory I've written here, and this is exactly the kind of thing one would write down on twistor space. Everything, the scalars just covariantly couple. The local operators of this theory are built from the scalars phi and gamma tilde, and the ghosts B and C. Great. The theory living on the defect of CP1, which is really the thing that's going to give us the self-dual gauge theory, just consists of bifundamental fermions describing d5 prime strings. So going from PT to Y. It's a very simple theory of just symplectic fermions. I got that right? Fermions, symplectic, or boson symplectic? One of the two.
Fermions can't be symplectic.
Yeah, the other one. Very simple theory of fermions, which couple covariantly to the bulk. This bulk world volume theory with this action. And local operators on the defect are built from those world volume scalars and ghosts that I mentioned on the previous slide, and these bifundamental fields. And of course, if they don't involve any of the bifundamental fields, then they're actually operators in the bulk theory, world volume theory, and we can just move them off the defect. And these are going to be central. So the ones we really care about are the ones that have got at least one of these fermions in them, so at least one psi. And the two most important operators are these ones, so J and J tilde. J describes a positive holistic gluon, and J tilde describes a negative holistic gluon. And it's easier to understand these with a picture. So we just take a psi, so these are psi's living on the CP1, and we bung a bunch of phi's in between them. And those phi's, if you remember, they lived in the anti-symmetric, traceless square of the fundamentals. They got two indices, so we're just kind of concatenating these as matrices. Each of these scalars, there are two options, and we can just contract them with the right-handed variable. So this depends on exactly the data of a hard generator in the Chiral algebra. The negative holistic gluon are very similar, but now we include a couple of ghost derivatives in the operator, which live in their adjoint. And I've only written two of the states, but it's possible to show that in the large n limit, we recover all the states of the self-dual QCD that you would expect. Okay, so I now want to go and compute some OPEs and verify that they match the collinear splitting functions that I mentioned earlier in the talk. So the tree-level OPEs are very easy to recover.
Could I study something like D5, D7 and recover SO groups?
I don't know what D7s, I think D7 saw some like
No.
quadruple vector or something. I'm not sure what they, and I don't know where to rack them, but maybe there's something fun to do there.
The gauge group of the theory in the bulk is not the group of the stack that's sourcing the field. So that one you make D7.
Sorry,
The probe brains make the probe brains D7s, and then you could
but if the probe brains are D7s and they can't wrap twistor space, right? They have to wrap something.
Yeah, a little bit. Or you wouldn't get twist. You have to twist space. That's what okay. So there's no way of getting it so groups here. No.
Not as far as I know. No. Not as far as I know. All right. So the the psi's have this very simple OP. I'm suppressing all the SPN indices. I'm just writing out the SPK indices. And they've got this very simple OP, just omega ij over Z1 minus Z2. If we put two of the J states together, so positivity gluons, we can contract those fermions at either end of the operator. And it's a very easy computation to do. You immediately recover the tree splitting amplitude. I should say in this step here, I've thrown away a whole bunch of terms which we're going to have to think about later. But at least if we assume that these phi's commute with one another, this is what we get. Okay. So to compute anything more interesting, we're going to need to know the contraction of two phi fields when we restrict them to the CP1 defect. So these are bulk fields, now just restricted to the P1. It turns out that up to differences in color structure, there's only one diagram we need to worry about. It's where we connect the two phi's through the bulk in a diagram with two external ghosts. And it's just a fact about holomorphic theories that this is the only thing that can contribute. You just need to look at basically the form degree of the propagators and see that there's nothing else that could contribute. Because this is an SPN gauge theory, the propagators so we can represent them by double lines. If you remember, these were in the antisymmetric square. And there are two possibilities. There's sort of a planar diagram, and there's a non-planar diagram. But also, because there are these two external ghosts, these can actually couple to either side of the propagator. So I really need to sum over all those possibilities. So here I've only illustrated sort of two of the possibilities, but there are, of course, four here, where the C's appear on opposite sides, and there are also four here. And that's contained in the following formula, but it's much easier to just look at the picture. And the B and the C and the gamma tilde are the same. So the simplest diagram one could consider, which involved both a contraction of phi's and a contraction of psi's, is a planar contraction of psi's. Now, if we do that, you can see that we form this kind of closed loop. And this closed loop has got no psi's in it. So that's a bulk operator. That's not something that lives on the defect. It can extend into the bulk. But I quotiented by all the fields in the bulk, except the constant one. So it's absolutely crucial that when I do this, I get no operators in that loop. So I have to just get a trace of the identity and a factor of n. And there are two contractions here, so that gives us a double pole. We've contracted phi, two phi's, that's what gives us the square brackets. As I said, I explained the factor of n. Turns out if you do the combinatorics, and crucially, this fact that the phi contractions are adjacent to the psi contractions gives us this particular structure for the splitting function. And if you look at this, you can see that there aren't the same number of lambda twiddle 1s and lambda twiddle 2s on the right as on the left. So momentum is not being conserved. And the reason for that is this is the collinear splitting generated by the brain back reaction. So the brain back reaction actually induces a kind of weird axion coupling in the self-tube QCD, which has the following form. So to see that, we notice that the stack of d5s, it sources a closed to one form field in string theory via the following equation. It's not too hard to, I should say, this has been done before. We aren't the first to do this. This is essentially the same as the Bern story. It's kind of a linearized version of the Bern story. You can solve for it using a Bochner-Martinelli kernel. The coupling of the closed string field to the d5 prime stack is just through this kind of coupling. And you can see here there's a kind of anomaly inflow going on, because the gauge variation of this term, it's going to give us sort of d bar of trace CDA, which we throw on the eta, and that localizes us to this defect, and that's sort of cancelling some chiral anomaly on this defect stack.
We also use this in the original paper with Kevin to give a level to the...
Right. So these fields are kind of appear all over the place in this celestial story. They're very good for cancelling anomalies, for example. Yeah, so this is kind of a standard construction at this point. And this Penrose transforms to a scalar on spacetime. And I think that's some result of some Twistor newsletter from eons ago, which you need to sort of dig out in the archive.
What is a nonlinear equation version of theta? It's just d by eta equals 0, then it would transform to a scalar. But
I think it
more
probably...
generally it would, I guess here it won't be water-Cartan, but still something.
I guess because the other fields are 0, it's kind
You
of
have a
linearized.
solution where all of the fields are 0, eta is the only thing, so it linearizes. And
Exactly,
that's-
yeah, exactly. So this is secretly, there's a 2-1 form, it's really a trivector, right?
That's a trivector, not one form, yeah.
Exactly, yeah.
So that's Gregor's number to be sourced. Log x squared there.
All right, I should say this is, of course, kind of unattractive. We don't usually consider couplings of this type, in gauge theory, but you can kind of ignore these terms because they only ever appear when a face is generated in one of these kind of string diagrams. Okay, but there's also a non-planar contraction, and if you chase through this kind of simultaneous psi and phi contraction, which is non-planar, you'll see that now there is no closed string state being formed. This is just an open string state. It's got 2 C's, so it's going to be a negative holistic Lorentz. And because there's no closed string state formed, there's no reason why these contractions have to be adjacent to one another. And that changes the combinatorics, the counting, and now momentum is conserved. And if you go through the computation, it's not particularly difficult, you'll find that this reproduces the one-loop splitting amplitude. So this is evidence now that the duality is operating at the quantum level. I also mentioned these non-factorizing terms. So these are maybe a little bit technical, but I think they're absolutely crucial to the whole construction. They come from 2 different places. I'm not going to go through the formulas, but I'll draw the pictures. So one obvious way to get sort of a bilinear term in the OP is to contract 2 phi's and to not contract any psi's, because there's going to be one open state and another open state. And here you can see one's positive and one's negative holistic. But this is actually not the only contribution. You'll find this doesn't match the non-factorizing terms. There's also this thing we already considered, but we weren't particularly careful with. And that was when we contracted 2 psi's, but we didn't symmetrize in the phi's. So the states have symmetrized phi's, and unfortunately they don't commute with one another. There's a constraint, a gauge constraint in the theory, which takes the following form, and in the presence of the defect, it's modified. And the extra term is this one, and this has the effect of cutting open a string when you try and commute 2 phi's past one another. So it can take this single string, cut it in half, and put 2 ghosts on one side. And if you take into account both those contributions, you'll find that you do exactly reproduce that formula that I had at the start of the talk. And in fact, that's actually how I got the formula. It's from doing this computation. All right. So I've now shown how to reproduce the one-loop splitting functions. I should say the Chiral algebra doesn't terminate at one loop. It has infinitely many corrections, loop corrections. I think they're at worst double poles, but it doesn't terminate, and I don't think at this stage they're not known. Maybe the simple poles in principle known by QU. But yeah, certainly we've not attempted to match them beyond one loop. But now I'm gonna change tack, and I'm gonna think about quotienting by a different ideal. So I mentioned that the bulk string states, sorry, not the bulk string states, the states in the world volume of Y commuted with themselves, and they commuted with everything on the CP1. So they're essentially just numbers. You can fix them to any value you like. I said before that I can just set them to 0, and that gave me this Chiral algebra in this axiom background, but you can set them to any other value. And if you do that, that's going to engineer for you an infinite family of Chiral algebras corresponding to a whole bunch of different self-dual backgrounds. I should say that in general, these backgrounds are actually singular, which is in some ways a plus, as I'll go on to explain. So here are some simple examples. So if you just take a trace of a bunch of phi's, you get axiom backgrounds. So I already described that the back reaction gave you this log profile for the axiom. If you bung in a bunch of phi's, you'll just get basically derivatives of that log profile. There are also these D5, D9 strings, gamma F, gamma tilde. There's a bilinear you can build from those, which is gauge invariant. And if you give that a background, it's going to engineer a certain SL16 flavor symmetry background. If you give a vev to this state, one trace of two C derivatives, you'll actually recover Bern space. And this connects this work to this earlier work by Kevin, Natalie, and Atul, and reproduces some of their results. And then finally, there's this very intriguing state. Unfortunately, it's the most complicated state, one of the more complicated states in the Chiral algebra, and it backreacts to give a Gucci-Hansen space. I've put an asterisk there because it's really some singular double cover of a Gucci-Hansen. It doesn't have this Z2 quotient we need to make it non-singular at the origin, on the CP1 at the origin. Unfortunately, sort of doing computations in this final case, which is the thing I'd most like to do, is extremely difficult. So right now, we're kind of stuck working on these ones because it's a lot simpler.
The gauge field background is preserve Lorentz symmetry in the R4 theory?
No. Right, and of course, one can basically take any combination of these things. There are many versions which are the modifications of these things. These are just some of the states. It's easy to sort of speculate about what kind of things you might be able to obtain this way. But I want to focus on one of them, the simplest one, which was this SL16 flavor symmetry. So giving a vev to this bilinear, turns out this has got it's a section of O2 over the CP1, and it's valued in the Lie algebra of SL16. So I just need to choose some appropriate section. And this source is a partial connection on the Calabi-Yau fivefold, where this partial connection is really describing the D9, D9 strings. And the sourced equation is this one. And you can solve that equation and find a particular SL16 bundle on twistor space minus the CP1 at the origin. And I don't know what this Penrose transforms to. It's certainly something singular. On space-time, it corresponds to a source, giving a source to a flavor symmetry background. And just to make life easier, I'm going to restrict the background to an abelian subalgebra. Makes computations much nicer. And I'm actually even going to do something even simpler than that. I'm going to assume that the section of O2 that multiplies that abelian generator has got a double root. The reason for doing that is there are some ambiguities in defining correlators in these backgrounds, and in this case, one could show that there's a unique definition related to renormalization of operators in 4D. So amplitudes in this background can also be understood, and are maybe better understood, as form factors in a theory where we make the background gauge field for the SL16 flavor symmetry dynamical. So I've here restricted to an abelian subalgebra, so it's a bit like making some Maxwell theory that couples to my self-dual QCD dynamical. And its fields are just going to be, of course, a connection, an anti-self-dual 2 form, the usual action, just abelian self-dual Yang-Mills. And if we bung in this operator and integrate out B0, you can see we get exactly this sourced equation. And so doing this background field computation is the same as doing this form factor computation. And then you can just go and churn the handle, do the computation. The simplest, or one of the simplest things to compute is the 1 + 2 fermion form factor, which has this kind of very nice formula, expression for it. It's crucial that we have no external photons because I'm sort of integrating out those background fields.
This is some nice hypergeometric sound.
I know, I don't think so. You might be able to get some, you bung it into Mathematica and it kind of sums it up, but it's not something you'd recognize. Well, maybe it's hypergeometric at this point, but I think if you go to endpoints, we can't write down a formula. We just have a recursive formula for the n + 2 fermion form factor in terms of the n minus 1 plus 2 fermion form factor. Right. Okay, so these are kind of nice, but there's kind of a neat trick we can do with these to access something that's a little bit more, I mean, all of these backgrounds are backgrounds in Euclidean signature, and there's no way that we can sort of analytically continue those to Lorentzian signature and make sense of them. But what we can do is we can kind of extract from this form factor computations form factors in flat space. So if we isolate the terms proportional to d squared in this expression, and we extract the SU2 left invariant part of, extract the SU2 invariant part, we actually get the form factor for B naught squared. So really all we're doing here is we're expanding this out to B naught squared. I haven't put D here explicitly, sorry. There should be a D here. Go to D squared, and then you sort of average over SL2C, and you get trace B naught squared. Or just B naught squared, I'm afraid. It's a Bealy. And it's a funny fact that it turns out that the result of this computation is the same if you replace that abelian subalgebra with a larger subalgebra. It's basically because this diagram is fairly trivial. There's no actual vertices of the background field theory which are involved. Similarly, if you compute the n plus 1 loop form factor of trace B naught squared this way, you get a very simple 2-loop amplitude in SLR plus SPK Yang-Mills plus pi fundamental fermions. So let me qualify this statement a little bit. First, this is like the most pathetic 2-loop amplitude you could conceivably compute. That's the first thing. This is really as simple as they possibly get. The second thing is, I've used the word amplitude here. The n plus 1 loop form factor, so I should say all of the external gluons are living in the SPK, so the SLR is all internal. I say amplitude, so the 2-loop or plus amplitude kind of these SPK gluons will split into a bunch of gauge invariant terms, and this is only one of the terms in that sum, but it's a gauge invariant constituent of an amplitude. It's something that one would need to know to get, say, the 2-loop or plus in a more general setting.
Are these 3 terms the same?
Pardon?
Are those 3 terms the same?
These, which 3 terms? These ones?
Yeah. There's some.
Am I missing something? This is supposed to be the, sorry, this is supposed to be the 1 loop or plus amplitude. So
That's right, it's permutation.
Pardon?
Permutation symmetric.
Right, sorry, sorry, apologies. There's probably some color structure I'm supposed to have here. You're right, and actually there's only probably one of these terms. I apologize, I've copied this down wrong. It evaluates to the same thing as the 1 loop plus amplitude. So in any case, from this computation, you can extract this form factor, and you can match it with some result in the literature for computing 2-loop or plus amplitudes, at least at 4 points. And because it actually matches the 1 loop or plus amplitude, it's not really a surprise to anyone that you can get this at arbitrary multiplicity. So it's, in a sense, it was already known, but nonetheless, it's very nice to match this via a holographic computation. And I'm sort of embarrassed to say this, but I feel like I should. You can take r equals 3 and k equals 1 in this formula. Okay. Right.
Getting the U1 size.
Ah, the U1, yeah. You're right, yeah. That's not quite what we do. Exactly. All right, so to summarize, I've reviewed how the self-dual sectors of certain gauge theories admit chiral algebras whose correlation functions reproduce form factors. I've shown that by exploiting twisted string theory constructions, you can get the chiral algebra for certain self-dual QCD as the large n limit of a chiral defect CFT by assigning vevs to bulk states, where bulk states mean states in the world volume theory corresponding to the bulk. This duality extends to sort of an infinite range of self-dual backgrounds, and we can exploit this to actually extract form factors. And this is another example of this kind of idea that self-dual celestial holography can be obtained through a combination of the twistor correspondence with twisted holography. So there are a bunch of future directions. So I've just described the simplest possible background because it was the easiest one to do computations in. But the vast majority of the allowed backgrounds have not been considered. And it would obviously be very interesting to compute amplitudes in these backgrounds and match them on both sides of the duality. Of course, it would be incredible if this existed beyond the self-dual sector, or even to use it to compute, say, amplitudes or form factors beyond just one step away from self-duality. Is there a similar duality for self-dual gravity? I think Atul told us a kind of a path maybe towards something like that. And finally, there are a whole bunch of variants of this construction that one could do. One Natalie already mentioned, which is to get the twist to use 2b instead of type 1. This will give you n equals 1 self-dual QCD for SLK. There are a bunch of more sort of stranger constructions one could imagine. Yeah, so there's loads to do in this direction. So thank you very much for listening. If you have any questions.
So you mentioned the unself-dual sector. So in the earlier works, at tree level, just trace b squared, if I'm not mistaken, gave the MHVM.
Yep.
So, but somehow, two insertions of trace b squared or something like this is not quite giving the NMHVM. So at tree level, levels are rational when one may hope that this kind of works. Is it because presumably there's some prescription, but it's not yet understood, or how to get the NMHVM?
Certainly, I mean, this Chiral algebra method won't let you compute the amplitude in the presence of two local operators at different points, which is what one would need, and then to integrate over the relative positions. And it's not even clear, or it's not obvious to me, that being able to compute it, you could certainly constrain that thing by knowing the 4D OPE. I mean, this is what Natalie was describing, knowing the 4D OPE of 2 trace b squareds, knowing that this has to be some rational function of the positions of those objects, trying to find that and then integrating over the locations of x and y. But that's certainly be hard, I think, or it's certainly something, probably would be an interesting thing to do, but I don't think anyone's done it, and it's certainly not easy.
Yeah, Kevin and I kind of got the CSW formula in our first paper with some asterisks, but
Right, because there's a term which goes like trace b cubed, and probably the most important one.
yeah, there's one term in the OPE that just is fixed by Lorentz invariance, and so we can get that one up to level easily, but yeah, for the OPEs, not known.
Since you can calculate these amplitudes on the Burns background, have you tried it on kind of multi-Burns metrics where you have?
Well, that's a great idea. I think that would probably be the best way would be to try and adapt the duality you guys have on Burns to sort of multiple stacks of brains. That would be the guess if you put sort of 2 distinct stacks of brains and try to backtrack them both.
So that should be cleaner than Noguchi-Hansen because the metric is you're saying you have to pass to a branch cover and work with a singular metric. For Noguchi-Hansen, the metric is an honest.
Absolutely. And in fact, I should say the reason you have to do that on Noguchi-Hansen is because on any Ricci flat background, your twistor space fibers over O1. And that means your scattering states, you can localize them at different points on the O1 base. And in a holomorphic theory, these just won't talk to one another. There's this kind of locality. And that means the amplitudes are immediately all 0 on, say, genuinely on Noguchi-Hansen. And so in a way, this is nicer because there are some things that one could match on either side, although, of course, it's a bit unfortunate that it's some singular asymptotically Euclidean background. Still would be interesting, I think, to see if that was possible.
Do you think so? Another thing that would be interesting to investigate, if you have a multi-Burns metric, I mean, there's a big parameter space of these metrics. If you just have a single center, a single generating two-sphere, then the only freedom you have is to scale the metric up and down. But otherwise you have moduli. And I don't know how explicit you need to know the twistor space or the metric. You can't get the generic metric completely explicitly. But I mean, for a big subfamily, one knows the metric exactly, and you have a very complete picture of what the twistor space is. But I would just wonder how those geometric parameters, should those geometric parameters in the metric influence the scattering or not?
I would have thought that they would. I would have thought the amplitudes would depend on that data. But,
That would make it more interesting.
absolutely, yeah. I mean, I think maybe we even looked at this briefly. Maybe others have looked at trying to do the multi-center Burns thing.
Simon did.
Simon did the, yeah, sorry, most of the calculations there, but somehow it wasn't as straightforward as, somehow to solve these equations on twistor space, you kind of, the trick is usually, you're trying to solve a nonlinear equation, and the trick is to write down a linear solution and then hope the nonlinear bit is 0. And if you've got multiple centers, that doesn't happen. And so probably there's something, I mean, surely there's got to be some clever way of doing it, but certainly we weren't clever enough.
Like in type 2b, people find multi-center extremal black holes. Some simpler version of that.
Here, the problem presumably you need to do it. You'd have Chiral algebras living on each of the stacks, and somehow they need to talk to each other.
Yeah, sounds a little bit like you've Higgsed the dual.
But 2 centers is not bad. I mean, that's the twistor space there was already worked out by Poon.
Yeah, but sort of the way these twistor spaces show up is you kind of write down these Beltrami differentials, and then you kind of, so that they're not holomorphic things, and then you find the holomorphic coordinates for them. It's very hard to sort of reverse engineer that, to sort of know what the twistor space is and sort of figure out how to reverse engineer it.
You know what the twistor space is after backreacting some sources in the flat twistor space, but you don't know exactly what sources to put in the flat twistor space and how that backreaction generates the twistor space that you know you're going to end up with.
So I would think that the linear solutions that are toric, I mean, these are, if you can set it up so the metric's actually toric. 2 centers, that's going to be automatic, but with more centers, it's more delicate. There's special choices. But then you could write down very explicit solutions to the toric linear equation, I think. Don't know if that helps.
That's scattering on the background.
Yeah.
But to generate the background itself, starting by putting some sources in flat twistor spaces, is the question. We can sort it. But further questions? Let's thank Roland.